So today we're going to talk about techniques for estimating the accuracy of a classifier or a prediction method. How accurate is your predictor? So give me a biomarker measurement so tell me your PSA level. I'll predict whether you have prostate cancer. How accurate am I in making that prediction? Can I believe I'm going to be right 92% of the time, for example? What's my sensitivity? What's my specificity? How do you estimate those things? Okay. So this chapter of the Introduction to Statistical Learning book has to do with two resampling methods, the first of which is really what we're going to focus on. So these are similar. We've met the Bootstrap already, and we've talked a little bit about cross-validation. They share a lot of things in common in the sense that they both are just resampling methods. So they're computationally intensive methods that use your computer to play some tricks to give you estimates that you wouldn't otherwise be able to get. The Bootstrap, I'm not going to lecture on the Bootstrap today because we've already talked about it a little bit, but the Bootstrap is primarily used for getting, for approximating the sampling distribution of a statistic. So, for example, from a sampling distribution for a statistic, you can get a standard deviation estimate, a standard error estimate. So suppose you want to do inference on the median survival time of people under a particular condition. Medians are different from means. They're not as easy to do confidence intervals for. Or maybe we wanted to look at a percentile, something kind of non-standard. I don't have a t-test. I don't have a t-based confidence interval to use for that. The Bootstrap is a very general technique that can give you a standard error and therefore a confidence interval for pretty much anything, regardless of whether it's a mean or something that has a formula-based result. The Bootstrap does have relevance to this classification stuff that we're talking about, classification and prediction. In particular, it can be applied to get standard error estimates of our coefficients in the model. So we're going to apply some model like logistic regression or linear discriminant analysis or something. And when you apply a model, you estimate coefficients of the model. What are the standard errors of your model so that you could get like confidence intervals and p-values for the gender effect in my prediction model, for example? Bootstrap can be used there. Cross-validation we're going to use for a different purpose, a completely different purpose. We're not trying to approximate sampling distributions. We're not getting standard errors or confidence intervals. What we're trying to do is estimate the accuracy of a prediction method. Okay, so let's keep going here. All right, we have seen this before, this difference between training error and testing error. We start these applications of prediction and classification with training data. These are data for which we know the value of the variable of interest for each of our individuals. Cancer or not, cancer class A, B, or C, stuff like that. They've been manually determined. Maybe a pathologist has looked at the tissue samples and said, these are cancer and those are not. And for each of those individuals, each of those samples, we have some omics data, a microarray or some next-gen sequencing data or a SNP array or something. All right, training error is what you get whenever you fit the model to your training data and then apply that model back to the training data. The model is going to fit the training data better than, it's going to tend to to fit the training data extra well because they were used to build it. If you were to go get a new sample, a random new sample of people with microarrays for whom you want to predict, do you have cancer or not, and apply the model to them, they were not used in building the model. They came from the same population, but their exact data had not been seen yet. When we apply the model to them, we get a more generalizable estimate of the accuracy. That estimate is what we would claim to apply in general. So my logistic regression model predicts cancer or not on the basis of a microarray. When I apply my model to the training data I use to fit the model, I get an accuracy of such and such. But I believe that that's going to be an optimistic estimate when you take this and apply it like in the clinic. So in the clinic, I estimate my accuracy to be something else. I want to estimate that something else. That's really what we want. In order to sell the public on, or on the doctors on using your classification technique, you need an accurate estimate of how frequently you're going to be right and wrong. Training error can often dramatically underestimate the test error, the generalizable error. This is a picture that we've seen, at least something similar. X-axis is model complexity. So are we going to fit a linear model maybe, or are we going to fit a curvy model that's more flexible? Are we going to do linear discriminant analysis, which assumes constant covariance between the classes, or are we going to be more flexible and do quadratic discriminant analysis, which allows for different covariances? Horizontal axis, going from low to high, is talking about more or less flexibility of the model. When you have low complexity, you tend to have high bias because most problems are not really linear. Linearity is a simple model that has some nice characteristics to it, but it's not generally expected to perfectly represent, complex systems in the real world. High bias, but low variance, because fitting lines is less susceptible to the specific collection of observations you have than fitting some complicated curve. Here's a sample of 100 people from a population. Let's fit a line to them. Here's a new sample from the exact same population. Fit a line to them. Those two lines are going to be pretty similar. As opposed to, here's those two samples, and let's fit like an 8th order polynomial. And then let's do it over here. Those are going to differ more because they're more sensitive to the specific data and the individual random variability that's in the data. High bias, low variance. And as you increase the complexity, you get lower bias because you can capture more subtle trends. And with that comes the high variance. And we have this distinction that we've talked about, training error, training error, vertical axis is prediction error, misclassification rate, or if this was a continuous response variable, that might be mean squared error. But our measure of error, with training data, as you make the model more and more complex, you get better and better fits, to the extreme where you just flat out interpolate the training data. No error. Perfectly reproduce every single observation. But we know that beyond a certain point, you're going to be overfitting the training data, resulting in increased error rates on the test or more generalizable group. So again, our goal here is to estimate the test error. Training error is easy to estimate. You just apply your model back to your training data. Test error, there's a little more to think about. So we're going to do classification of prostate cancer, yes or no. Which model should we use? Should it be a real simple linear model, or should it be a more flexible, polynomial model, or a neural network or something? What we can do is try a variety of models, and for each model, vary a tuning parameter or two, and estimate that red curve for all of them, and go pick the one that seems to correspond to the minimum test error. The simplest and most ideal solution to estimating the real generalizable error rate is to have a distinct pairing of data sets. Here's a big data set that is training data because I know the answer for the variable of interest. Here's another one, another set of data that I have the same information for. These could also be used as training data, but what I'm going to do is only use the first as building the model and hold out, set aside the other one as a designated test set. And then to estimate the generalizable error rate, you fit the model with your training data, apply the fitted model to the held out data, and compare the predictions on the held out data to the truth, because you know the truth for those held out data. That difference, those errors, will give you the estimate of what we want. That's the generalizable error rate. The problem with that solution is that you have to have two big data sets. Data costs money, costs time, and in bioinformatics applications, every sample is expensive. And so it's kind of hard, it can be hard to sell to the lab people and the biologist whose grant is paying for all this, that, okay, you plan to get, you wanted to get a sample of size 200 to build your classifier of breast cancer or whatever. Go ahead and make that 400, because you're going to need a whole other data set. What are we going to use that other data set for? Nothing, just to estimate the error rate at the end of it. So there is a kind of a premium or a desire to do something a little more efficient. Okay. So in the absence of this kind of luxury of having a large held out test set, let me go forward a little bit here. This is still talking about that validation set approach, test set. Okay, so a technique that allows us to estimate that generalizable error rate without having to sacrifice a large data set only for estimation purposes is cross-validation. Very widely used. So any, if you go to SAS or JUMP or any mainstream statistical software package like that and ask it to do some kind of predictive model, it's going to be an option in there somewhere, an argument that allows you to say cross-validation. Do cross-validation. What is cross-validation? Okay. So the idea of cross-validation is to kind of mimic what we were talking about originally as the ideal solution. If we could have two data sets, training, testing, then we could estimate the generalizable error rate. What cross-validation does is, let's follow the slides here, let's break the data into capital K equal-sized groups, 5. Split our training data into 5 equal-sized parts. In the first part, there's some representatives of each of the classes we're interested in. In each of the K classes, there's representatives of the different classes. Take one of those capital K parts and set it aside as if it's the test data. Hold it out and use what remains, the remaining K-1 parts, to train the model. Apply that model to the held out subset. That gives you an estimate. How many errors did I make on that particular held out subset? Suppose I made 5. Now go back and pick another one of those K parts and make it be the test set, and bring what you had been calling the test set back in here and treat it like one of the training samples. So now I'm like at iteration number 2. There's a new test set. There's a new K-1 parts of training data, and redo the whole thing. Fit the model, apply the model to the new test data. How many errors did you make? Maybe I made 7. Do it again, do it again, do it again. 5-fold cross-validation. I made 5 errors in the first fold, 7 in the second, 4 in the third, and so on. If you average up those errors, that's an estimate. It turns out that's an estimate of the generalizable error rate. Even though it's kind of cheating in a way. We used the training data for both training and testing. At the end of that process, all the training data that's all we used for training and testing. The key is that at each iteration, we didn't. We only used a subset with a held out piece. And it turns out mathematically, kind of magically, that the result is at least nearly unbiased. There is some bias still, but it's much better than just using the training data, like a resubstitution error rate. That's K-fold cross-validation. So you would, that's the picture for it, divide up your N samples or individuals, your human beings who you want, for whom you know prostate cancer status. Take your 100 people in your sample and divide them into groups of 20 randomly. Iteration 1, you take the first 20, set them aside, and use the remaining to fit, and then apply to the set to held out. Repeat. Now the second batch is held out. Repeat. Now the third, and so on. Yes.
Do we take all the 4 beans as training set, or we do compute the classifier for each bean and then we?
So iteration 1, the red box is going to be set aside for training. For testing, and boxes 2, 3, 4, 5 are pooled. They're put all together. And that entire collection is used as the training data at that stage.
Do you randomly decide what's in the validation set?
You should randomly assign, if you had 100 people, you would randomly scramble their indices so that you would randomly pick who goes in which of these categories.
What if you find that you have some population structure in your training set? After you choose it and then do the analysis and you realize, oh crap, I've got population structure.
Like structure that came about because of how you divvied them up here, or structure that was in the population?
Structure, meaning certain ones are more unique than others.
So suppose there is some structure, some relationships, some correlations between the individuals. That's a not advanced stage of cross-validation, but that's one step further in detail. What we're talking about here, we're essentially assuming that all of our individuals are independent of each other. You can just randomly move them around, you're not hurting anything. If, for example, instead of 100 people, we had 20 people, and each one of them was measured 5 times, then that's different. That's an issue. You wouldn't want to just randomly scramble necessarily. So what you end up doing, that case is easier to describe than the one you described. Suppose there's just 5 observations on each of the individuals, then you would pick up groups of observations by individual. So instead of randomly shuffling the columns, you would randomly shuffle individuals. So I picked individual 4 to go in my training set. That means all 5 of that individual's columns got picked. So if there's structure, if there's correlation, the answer is to make sure you do the scrambling and the shuffling and stuff in a way that preserves where you think the structure is. Correlation is kind of easier to talk about. If it's like measurements over time, you just pick up the whole profile for an individual.
So keep people or the individuals that are grouping together, correlations once you've done your kinship matrices and stuff. Try and keep those together in the validations.
Yes. Try to keep correlated things together. That applies to the Bootstrap as well. You can apply the Bootstrap very generally to get confidence intervals for anything. And one of the selling points for that is that it can be applied to correlated data. You don't need to, t-tests and simple linear regression, they break with correlated data. They're not applicable without some sophisticated math on top. The Bootstrap can be brought in and just applied with very little math, just a simple little R loop, as long as when you sample with replacement, you keep the correlations together. So sample individuals with replacement as opposed to just columns. Yes, so that's what I meant by more math on top that you had to use. So an alternative with correlated data would be something like generalized estimating equations or random effects models, which, having seen them, they're a little bit complicated. They're not hard to use because you just call a function in R, but the Bootstrap is conceptually very simple, and you could do it, manually pretty easily. Even if there's not a function for the method you want to use, you could do it yourself. So the cross-validation based estimate of the error rate is, roughly speaking, the average of the error rates that you got for each of the folds. 5-fold cross-validation, I get 5 error rates. I got one when I treated the first block as the holdout data. I got another one when I treated the second block, and so on. So my overall estimate of the error rate is a weighted average of those K ones. This MSE is talking about numerical response. Remember that if we have categorical response, like cancer versus normal, then it's not mean squared error, it's a misclassification rate. But a couple of slides further down, we'll see it's the same idea. The CV-based misclassification rate estimate is a weighted average of the CV-based, or of the estimates for each of the K folds. K-fold cross-validation is what we've just defined. For example, K equal 5 would be break the data into 5 groups. K equal 10 is another common choice. One other common choice is K equal to N sample size, which means each time you create a validation set, a held out test sample, there's only one individual in it. It's very easy to code. It's called leave one out cross-validation in the sense that you only left one out at a time. Okay, we'll comment on which of these is best. Should I do leave one out cross-validation, or should I do 5-fold cross-validation, or 10-fold, or what? There are some general principles that can guide that we'll see. Skip that, skip that, skip. Skip. No, we'll do this one. There is bias. Cross-validation is not strictly unbiased. It's much less biased than resubstitution. That is, just applying the model to the training data. And not every K-fold method is equally biased. So in particular, if K is equal to 5 or 10, there is some upward bias. You overestimate the error rate. Not the end of the world. You'd rather overestimate it than underestimate it, probably. But there is some bias. You minimize that bias by doing leave one out cross-validation. But we've seen earlier in these slides that error rate or overall accuracy is a function not just of bias, but also of variability. We talked about that mean squared error being written as bias squared plus the variance. Leave one out cross-validation, low bias but high variance. As in, here's 100 people for whom I have microarrays and I know cancer status. Let's apply leave one out cross-validation and logistic regression. My estimated cross-validation based accuracy or error rate is whatever, 10%. Now here's a new sample of 100 people from the same exact population, and we'll do the exact same thing. Logistic regression, leave one out cross-validation. That resulting estimate, highly variable. That's what we mean by high variance. So even though it's unbiased, it's highly variable. Statistical performance or operating characteristics are usually defined in terms of long-range averages. If you want to estimate the mean income of everybody in Texas, go sample 300 people and compute the average of their income. That's unbiased. As in, if you increase the sample size to the whole population, you'd be exactly the right answer. But there's also variability. Here's 100 people or 200 people, and I estimate their average. I get their average income. Here's a new set of 200, and another one and another one. Suppose you drew a histogram of lots of those estimates. How variable is your estimate? That's like standard error type of concept. So, long story short, k equal 5 or 10 is what I've seen generally recommended as kind of like the rule of thumb, best choice for balancing bias and variance. Not always super easy to do that in practice. Leave one out cross-validation is really easy to do. It's just one for loop, for I and 1 to n. Hold out 1, use the remaining n minus 1 to train. If you wanted to do 5-fold cross-validation, suppose you had 21 individuals in your data set. Okay, divide that into 5. Oh, doesn't divide to 5. Issues like this correlation stuff, how do I keep things together in groups like this, can be a little bit tricky. If you have the option, say in R or SAS or whatever, would you like to do leave one out cross-validation or 5-fold cross-validation? I would always pick 5.
Does it cause problems if you don't have a divisible population size?
It's not a problem if they don't divide evenly. At the end of this, what we do is a weighted combination of these, where this is how many were in that K, in that group. So this allows for unequal numbers in the groups. If they are all equal, then it's just a straight average. Those slides that preceded were strictly for regression problems where you have a numerical response, but cross-validation applies just the same exact idea to classification problems with a categorical response. So that's what this slide is saying. It's a summary of what we saw up above. The overall cross-validation estimate is a weighted average of the error rates that we saw in each of the K folds. This is an important point. We've talked about this issue of having lots of features, thousands or millions of features, SNPs, genes, microRNA, whatever, and we want to predict some, cancer, say. Chances are, I don't need all of my thousands of features to have a good predictor. In fact, chances are, many of the predictors are only going to hurt because they don't have anything really to contribute. They're not discriminatory. If they're not going to contribute anything, if they're not going to help, you don't want them in the model because it's going to drag down the accuracy of your model. So feature selection, you're doing that in your homework right now. You start out with some number of total predictors, maybe 5,000, and we want to find just the top so many. So maybe just the top 100. What might you do? How do you do feature selection? The idea is to find the top, or maybe rank the features in terms of their discriminatory information. In the context of a numerical variable, a numerical response, like, I don't know, cell count in your colon or something, I don't know, some kind of aberrant cell count in your colon. We want to predict that number. We could compute a correlation, say, between gene 1 and that number, and a correlation between gene 2 and that number. If a gene is highly correlated with that number, it is informative. I can predict that number with this gene. So we might, for example, go find the 100 features that have the highest correlation with the response. Same idea in a categorical case, classification case, cancer versus normal. Let's find the 100 best features. We could, for example, do a t-test or something for each of the features comparing cancer to normal and get the p-values or the test statistics themselves and order them that way. This one had the smallest p-value out of all of them. The expression levels for this gene in cancer were very different than those in normal. So I want that feature in my model. Okay, so suppose we did that. Suppose we went through our 5,000 genes. We did a t-test each time. We ranked them in terms of their p-values, and we picked the 100 that had the smallest p-values. In our training data, we did a loop, did a bunch of t-tests, pulled out 100. Okay, now let's classify. Let's build, say, a logistic regression model to predict cancer versus normal. And we're only going to use those 100 predictors. We picked them because we think they are the best. So we're only going to use them. What is the accuracy? How would I estimate the accuracy of this model? So the main point here has to do with where do you apply the cross-validation. Cross-validation just means here's training data, split it up into k groups, and go one by one, train, test, train, test, train, test, average those results up. One thing I could do is only start here. So I did my feature selection. I picked the 100 best genes. Now let's do classification. So my training set is 100 features only. And now let's do cross-validation. Let's assign the columns into 5 groups, and within each of those cross-validation folds, we'll fit a model using these 100 predictors. Apply it back to the held out fold, average up the error rates. That is, it turns out that's a wrong approach that gets used a lot. In fact, I read a paper today, 2016 publication in the journal Gut, which is high impact factor. As far as I can tell, that's what they did. So the problem, the question that they left us with here is, can we apply cross-validation in step 2, forgetting about what we did in step 1? And the answer is no, because when we did the feature selection, we were essentially using the data. We were using the training data. Cross-validation needs to reproduce the entire process, everything you did, ideally, to the data, from raw data to classification. In step 1, you have used the data. If you don't incorporate the fact that you already used the data, it's an overfitting issue. There's the potential that you have kind of overfit your data. Like when we do t-tests. What's up with the t-tests? We compute a t statistic, sample mean minus what we think the mean, well, let's do a two sample t-test. Those are prettier. Sample mean in group 1 minus sample mean in group 2. Divided by a standard error estimate. So let's assume the variances are equal, and we'll do a pooled standard deviation times 1 over sample size for group 1 and 1 over sample size for group 2. Two sample t statistic. We compare that, the reference distribution, the null sampling distribution, under the null hypothesis, we say this is a t distribution with m plus n minus 2 degrees of freedom. Where does that t come from? Why in particular is it not z? You learn in Stats 101 that if the sample size is big, it's essentially z. With large sample size, standard normal, these are about the same for large m and n. The distinction between z and t has to do with the fact that in this model we had to estimate something. Before we could compute the statistic, we first had to look at the data and compute something. So it's like we've used up some of the information in the data. By looking at it and estimating something that we then used, we've used up some of the data. It's also similar to the degrees of freedom thing. How many degrees of freedom do you have when you do ANOVA, for example? You have n observations, but at the end of it, you don't say you have n independent pieces of information because you had to estimate some stuff. You had to estimate the means for the different groups, for example.
And that could affect the bias, can cause the bias and variance, more variance.
Yes. So if you don't account for this type of issue, for example, in a t-test, if you looked at the z distribution instead of the t, in this case you would have bias. Actually, not bias. What would you have? The probabilities would be incorrect. In the classification context, it can translate to bias and variance. Usually what it translates to is extreme bias, because you start out with thousands of features, you boil them down to a much smaller number. They were specifically picked because they're going to be good in the regression model. They're the best you're going to be able to find. So then if you just treat them like that's what you sampled from the population, you're going to have an overly optimistic estimate of how accurate you are. So what you should do is apply cross-validation to the whole process. What that looks like is not this. So this picture is meant to say we get our training data, and step 1 is we do feature selection. Then we do cross-validation and classification. The correct way is to do cross-validation, and inside each cross-validation fold, you do the whole thing. So I had 100 observations. We randomly broke them into 5 groups of 20. So cross-validation fold 1, iteration 1. I have a training set of 80 and a test set of 20. On that training set of 80, let's do feature selection. T-tests for all of the thousands of features, rank them by their p-values, pick the top so many, put those into a logistic regression model, get an estimate, get error rates. Inside the fold, inside that cross-validation fold, we did the feature selection. If you don't, then the final cross-validation estimate of your error rate is wrong, and it can be badly wrong. It's going to tend to be overly optimistic. There were a lot of papers that came out in the early days of microarrays that said, 100% accuracy in predicting breast cancer using 2 genes or something. I had one of those papers. And there were, lots of noting of why don't these things translate to real clinical biomarkers very often. There's not many biomarkers that have come out of those types of studies. A lot of it has to do with inaccurate estimates of error rates. It looks like you did wonderfully, but that's because you kind of hijacked the process. You cherry-picked the features out of a huge list and then treated it as if that was what you sampled from the population. So it makes it look like you had a great predictor. Long story short, make sure, if you're going to do feature selection, make sure that the feature selection goes inside the cross-validation folds. In the homework, you're doing that. That's why it takes a long time to run it. So homework 6. For naive Bayes, you're going to do feature selection. We had 2,000 features, I think, with these data. Yeah, 2,000 features total. But let's consider a variety of feature set sizes. Maybe I only need 1 gene, or maybe 2 is sufficient. Let's try 1, 2, ... 300. For each one, get a cross-validation estimate of error. So for each one of these choices, you need a cross-validation, an entire cross-validation loop. And inside the loop, t-tests, p-values, rank them, pick the best so many. Fit the model with those so many, and apply it to the held-out observation. All right, so questions about cross-validation. Yes?
For choosing how you, the general idea is that they differ in terms of variance, and that so we have to, it's better to work with 5 or 10.
Yeah, so for what should K be, if you're going to do K-fold cross-validation, I'm telling you to do leave one out cross-validation here. That's mainly just because it's easy to do. It's really easy to do. But the trade-off is, so should K be equal to 5, 10, N, what should it be? It's a question of bias variance trade-off. So as you go from left to right here, so bias will increase. Let's see how to draw that. Bias increases as you go away from leave one out, but variance increases as you go towards leave one out. And overall, what we care about, like a mean squared error, is the bias of the method squared plus the variance of the method. So the trade-off isn't always clear which one is going to be best, but what the authors say is that often that does best here. Even though those come with some bias, you're willing to swallow some bias if it drops down the variance substantially enough, because that translates to overall a better accuracy for the classifier.
But with those, we have to be careful about the structure in the data, right?
With
how to pick, for example, if there's correlation in the data.
Yeah, so if you're going to do cross-validation, even if it's leave one out cross-validation, you need to be aware of possible correlations between the individuals. Yeah, because suppose you had 100 observations, but it was 20 people measured 5 times, it could be that in one of the folds you get one person. Well, yeah, the correlation can make it so that randomly splitting them up can break the real relationships that are there, break the structure that's there. So if you have structure, ideally you estimate it, represent it somehow, and mimic it whenever you split into groups, whether you're doing cross-validation or Bootstrap. The last several slides in the notes here, I won't lecture through them, but if you're interested, they talk in some accessible language about what the Bootstrap's all about. So again, these guys created the Bootstrap mainly Brad Efron, but Efron, he's at Stanford. These guys are all at Stanford. Tib Shirani was co-author on the Bible of Bootstrap, which is called Introduction to the Bootstrap. So yeah, have a look. Bootstrap, they talk about this a little bit, but Bootstrap is primarily recommended as a method for estimating standard deviations. They do at the end here say, or consider, what about using it for estimating accuracy of a classifier? It can be used instead of cross-validation, but cross-validation, it turns out, is a little bit better. This slide is relevant to what we were talking about earlier. In more complex data situations, figuring out the appropriate way to generate Bootstrap samples or randomly sample, like cross-validation, can be complicated. For example, if the data are correlated, time series, that means multiple measurements on the same individual, you can't simply sample the observations with replacement. And it's because of what we've been talking about. If you did that, then the population structure is broken whenever you sample. So you're not going to be able to make inference to the population. And so that they say here is analogous to what I was saying earlier. If you could create blocks of correlated observations, preserving the structure, sample those. Yeah.
Isn't that the case for cross-validation as well? I mean,
Yeah, I need to think about that. In cross-validation, let me think about that and speak to it next time. It's actually kind of rare. I can't think of many examples where we do prediction with correlated inputs. So I'll think about it. All right, we are out of time. Let's see. Primarily used for standard errors. Standard errors can give us confidence intervals. Where did they say something about error rates? Can the Bootstrap estimate prediction error? They address it a little bit here. Long story short, cross-validation is better. All right, well, that does it for today. Any more questions? Some of the codes? Wednesday, we'll do that. Wednesday, I'll go through some code. The place we'll go is the con data. This has illustrations of most of what we're going to be doing. So we'll go through this. Let's see, do we have cross-validation? This is cross-validation. So this is the con data, and we're going to do feature selection and k nearest neighbors classification. We're going to do k-fold, 5-fold cross-validation. No, I think we're going to do k equal 5 for the k nearest neighbors. And we're going to do 5-fold cross-validation. So here's an illustration of just the practical issues of doing this. We have 4 classes, and there's not equal numbers of individuals in the classes. So I manually picked in fold 1, give me 2 individuals from class 1, 6 from class 2, 4 from class 3, and 5 from class 4. And I picked these numbers to, they're not all the same, but they add up, they use up all the samples. Then randomly assign to the 5 groups. And here's cross-validation. So for 5 iterations, pull out testing data. That's 1/5 of the data. And training data is what's left. Apply a test statistic and rank the features in terms of discriminatory information. I used an F statistic. And then for each of the possible feature set sizes you want to consider, this is within the cross-validation fold. For every single feature set size I want to consider, I'm going to do the whole thing. I'm going to fit the model, apply the model to the held out data, get an accuracy estimate. And at the end of all of that, my final cross-validation based estimates are averages of the K individual estimates. So Condata has a lot in there. Some of this, will be easier with me talking through it, but we will talk through it on Wednesday. Okay? All right. See you then.